Okay, in this video, we're going to learn what ERPs are. And this presentation was made possible from materials from Pursue. So check them out, pursue.erp.com. So after watching this video, you should be able to explain how postsynaptic potentials create a neural dipole, explain the factors that affect the summation of neural dipole, explain how location and orientation of dipoles affect the distribution of voltage on the scalp, and explain how noise in ERP data can be reduced by averaging multiple trials, and understand the graphs, the various visualizations that we can do of ERPs. So this gives you an overview of the first part of this video presentation. What we're going to do is first talk about what ERPs capture in terms of the neural activity, then how that forms a dipole, how those dipoles are added together, and then how that spreads to the scalp, and we record it in the form of EEG. So first, let's talk about the fact that the EEG captures postsynaptic potentials, not action potentials. So hopefully you've already had biopsychology. If not, you can talk to me about some referrals to other videos or other material. But the postsynaptic potentials are happening primarily on the dendrites, maybe around the soma, where the presynaptic cell has released neurotransmitter and is opening up ion channels, and ions are flowing into the postsynaptic neuron. So these slower so-called graded potentials create a sustained activity, electrical activity, that can be added together and create a measurable signal. The action potential is pretty rapid and brief, travels down the axon, and so that's too rapid and too brief to be recorded in most situations. I will say that if you want more detailed information on dipoles, go to the Steve Luck Chapter 4 videos, Generation to Propagation of ERPs. He goes over this in much more detail. This is a pretty superficial description here, just so you have an idea. But the idea here is that we're having activity happening either in excitatory postsynaptic potential or inhibitory postsynaptic potential on our dendrites. And so that's going to create a current, which is, at the dendrites. And so to close the circuit, there's going to be the opposite charge. So in this case, we have a negative charge at our dendrites. And to close the circuit, we would have positive ions accumulating at the soma. And so that would create a dipole. And in this case, a dipole which is sort of, faced downward, right? But our dipoles could be faced downward, as in the case of this example. They could also be faced upward, just depends on their location and the source of the activity, whether it's excitatory or inhibitory. Now remember, we're not recording one individual dipole, we're recording the summation of many neurons or tiny little dipoles that summate and can be recorded at the scalp. The dipole will be strongest when the neurons are aligned in a similar orientation. The signal could be canceled if we had neurons that are in opposite alignment, so this could happen and we would fail to record anything in that particular case. Or the dipole could be weak if we had neurons that were sort of randomly aligned in particular tissue, right? So keep that in mind as well. It's not a perfect recording at the scalp. When all of these individual dipoles add together, we call that an equivalent current dipole. And in these slides, you're going to see, and actually in a video a little bit later, you're going to see that the round part represents, in this case round in blue, represents sort of the negative charge, and the pole of the dipole represents a positive charge. In some cases, people represent these as arrows, where the arrow would be, the arrowhead would be the positive charge, and the arrow base would be the negative charge. So over here, we see the equivalent current dipole, which is the summed orientation of the synchronously active neurons. And the active neurons are aligned at 90-degree angle, so the dipole is upright. But in this other example, half of the neurons are at 90 degrees and half of the neurons are at 0 degrees, and so the dipole is oriented at 45 degrees. So this just illustrates that our dipoles can have different orientations depending on the underlying source of the current. So that brings us to understanding the scalp distributions. The spread of these dipoles spread through the brain and are recorded at the scalp. So in a second, I'm going to show you a little bit of a video that simulates this. And so while you're watching the video, think about the answers to this question, how the dipole location affects the scalp distribution, because you're going to see the scalp distribution, and I'll explain how that looks in this video in just a second, and how the dipole orientation affects the scalp distribution, right? So the scalp distribution here in this video is represented by these concentric circles, right? And the stronger the signal is, the more circles there will be. The weaker the signal, the further apart those circles are going to be. And you'll also notice that some of the circles are red, that would indicate positive scalp polarity, and some are blue, that would indicate sort of negative scalp polarity. And you can sort of see how they change, both with a sort of coronal view and a horizontal view of the person's head as this dipole changes. So now the dipole itself, the circle is going to be the negative charge, and the line would be sort of the positive charge. And you're going to see the video is going to go through moving it sort of like front to back, left to right, top down, and then it'll change the orientation of the dipole, and you can see what happens to the scalp distributions. So here it is going from the top to the bottom, so the dipole is getting deeper in the brain. And here the dipole moving left to right. Now you're seeing a demonstration of changing the dipole orientation. And the last one is the front to back dipole change. So how does the dipole location affect the scalp distribution? So when you saw it go from top to bottom, it changed the strength of the scalp signal. So the amplitude of the waveform, left to right, shifts the sort of the positive and negative scalp values across the hemispheres from the left to right. And then when you saw the dipole orientation, that changed the positive and negative around the sphere, around the head itself. So understanding the EEG waveform, so it, of course, tracks changes in scalp voltage over time, right? So in this diagram, you're seeing blue representing more negative values and red representing more positive values at a particular scalp electrode. On the ERP traces, you'll see microvoltage plotted as the y-axis, time on the x-axis. The T3, T6, these are just time intervals for this particular graph, but you would see that displayed in milliseconds for ERPs. So it's just plotting here the values over time so that you can see the change in scalp activity that corresponds to the picture above. So just like a cocktail party, there's lots of neural conversations going on simultaneously in the brain. So to record cocktail party conversations, we could place several different microphones around. Microphones would capture the summed sounds that are coming from the sources of those sounds, the people. And each one would record a little something different depending on their location, their distance, their orientation, etc. So the electrodes are very similar to these microphones. It's going to capture the sum of the neural activity that reaches the scalp, just like the cocktail conversation recording. So each electrode is going to record a slightly different signal depending on its location, distance, and orientation with respect to the neural sources. So factors that influence the EEG signal strength and polarity. First factor is the electrode location. Obviously, if you had a neural dipole or neural source like is pictured here in this diagram, the electrodes over the left are going to have a different value than the electrodes on the right. The dipole distance, how far away it is from the dipole, right? Remember, the strength increased as the dipole got closer to the scalp itself. and the dipole orientation is going to influence that. So all of these things are going to influence the recording at the scalp. So the ultimate goal of ERP data is to use the physical properties of the waveform to make some inferences about maybe neural dipoles and cognitive processes in other cases. So researchers don't really get to see the actual neural dipoles. We have to infer them from the physical characteristics of the waveform itself. So we're going to dive into that. So the first thing that we have to understand is that we have to average the EEG signal to reduce the noise. So what is the noise? The noise are lots of peaks and valleys creating this jagged look to this waveform here. What we're going to do is average across the same trial types to reduce the noise and form the event-related potential. So here's an example to illustrate this. The oddball paradigm. So the oddball paradigm presents some standard stimulus, in this case a black circle, then presents an oddball, the target, in this case a red circle. And so participants press one button if it's a standard, another button for the rarer targets. And so these trial sequences will continue. So let's look at the EEG from this oddball paradigm. And you can see that we have two trials of standard, and there's EEG, and that gets averaged together and plotted in a trace down here in this black line. And then we have one trial where we have the target, and that's plotted, the EEG activity is plotted as the ERP activity is plotted as a red line in this graph below. So with just two trials for one ERP and one trial for the other ERP, that creates a pretty noisy situation. If we increase it to 10 trials, you'll notice that it gets a lot smoother and looks a little bit better. And if we go out to 20 trials, even clearer, and 40 trials, much clearer, less noise, much more signal being captured in that ERP. So averaging increases the signal, decreases the noise, something that we call the signal to noise ratio. So let's talk a little bit about the physical characteristics of the ERP components. So ERP components are deflections, right? Peaks and valleys in the waveform that reflect, remember, they're reflecting the summation of this neural activity in response to some event. So time zero is when the event actually happens. For example, we have an ERP here labeled the P3. So they get their name, P for the polarity either being positive or N referring to a negative potential. The order, so sometimes P1 would be the first positive waveform, N1 would be the first negative waveform, and so on. You could have N2, N3, etc. Another example is sometimes the components are labeled by their time that they happen. So sometimes people call this ERP the P300 because it peaks around 300 milliseconds after the stimulus. Now the waveform plot shows the changes in electrical activity at this electrode over time. Could be a single electrode. Sometimes it's a collection of electrodes, average, so you'd have to look carefully at the figure to interpret that. Positive is up in this graph, but sometimes people plot negative up as well. And so you have to be aware that that's going to change the polarity of the waveform, so you want to take a look at that. We also have topographical maps. So the topographical map will show you, in this case, an interval, P1, across voltages across the scalp. And so we can see that the blue represents more negative voltages towards the front of the scalp, because you can see the nose here, and red represents more positive voltage towards the back of the scalp, in this case the occipital sort of area. Now we could plot this also for the other components, and you'll see that the topography differs depending on which component we're looking at and which one we're talking about. Keep in mind that these are scalp locations, not brain locations, so it's fine to sort of talk about the parietal electrode sites, but it's not parietal tissue necessarily. Something we'll learn about in another video. Identifying the neural source is difficult with ERPs. I also pointed out that those components had different scalp distributions, right? So the P1 is more posterior or occipital area, N1 more frontal, and then the P3 more posterior, right? So the scalp distribution represents different time frames, right? So your topographical maps are going to show some sort of time frame. A lot of times they'll plot differences in conditions over that time frame, and they show us which electrodes have the largest amplitude for a particular component. You can see the white boxes here are indicating whether it be positive or negative, the maximal amplitude at those electrodes. Amplitude and latency measurements for a component are typically reported on the electrodes that have the highest amplitude for that particular component. So on that note, measuring the components, we can measure the amplitude. So this is the height of the waveform. We can measure the latency. When does it peak, right? And we could look at the scalp location. So these are all different measurements that we can take in our ERPs. So just to bring all of this home, or this discussion home, let's say that we have our oddball paradigm and we have an ERP for targets and standards. How would you describe the difference between these? Hopefully you're quickly gathering that the amplitude of the P3 component seems to be greater, taller for the targets than the standards. But the time frame the peak seems to be pretty similar, around 300 milliseconds. So some take-home summary here. The raw EEG data contains signal and noise, and so we're going to average to bring out that signal and that noise. Waveform plots or trace plots show the voltage over time at individual electrodes. Topographic maps, on the other hand, show across the entire scalp for some single time point, or most often like a range of times. And the component can be measured or described by amplitude, latency, and scalp location.